Hey guys, so in the last lecture of magnetohydrodynamic power plants MHD, we have seen the concept that how MHD works, that how the directly the energy is converted into electrical energy, that kinetic energy of the particles are converted into electrical energy. So that we have seen. So today we will see the thermal efficiency of MHD cycle. So in overall power cycle, a compressor is used to elevate the pressure. Heat is added at a high pressure and flow is accelerated before entering the converter. So let's draw schematic diagram. So suppose this is an heater. So here heat is being added. So suppose QH amount of heat is added, then it moves towards the expander, that is generator. So here the electricity is being produced. So this is we will call as generator. So here it is coupled with a resistance of load RL, and here from here the power is being produced from the generator. Then this will move towards cooler, so COOLER, cooler. Then the gas will move towards the compressor. So this is the compressor. So here work has to be done. So WC, and then it will move towards the heater. So let's say this. Let's divide the cycle in 1, 2, 3, and 4 stages. So now let's draw the TS diagram for this MHD cycle. So suppose on the x-axis is entropy, it is S, and on the y-axis is temperature T. So if we draw the TS diagram, so we'll get that. So from 1 to 2, so 1 to 2 processes, heat is being added, so temperature will increase. Then 2 to 3 is power generation, so temperature will reduce at constant entropy. And then 3 to 4 is again cooling process, so the heat is being rejected. And then 4 to 1 is compressor process, so the temperature will increase. So let's say 1, 2, 3, and 4. So this is 1, 2, 3, 4. These are the uh, so this is an ideal cycle. So let's give the real cycle. So just for the ideal cycle, we'll just rename 1 as 1 dash and 3 as 3 dash. The real cycle will be somewhat, 1 will be here and 3 will be here. So this will be the real cycle. So the overall efficiency of MHD power cycle is limited by a Carnot efficiency. So in terms of TS diagram, so we'll write as efficiency is equal to work output upon heat input. It is output upon input. So let's do the work output. So where we are getting the output? So output we are getting in the expander, that is generator, that is 2 to 3 process. So we will write here as h uh, h uh, h02 minus h03. So this is the work output minus work input. So we are giving input in the this compressor, so that is 4 to 1 process. So we'll subtract it as h01 minus h04. And what input, heat input we are giving? So heat input we are giving here in the heater, so that is 1 to 2 process. So that is h02 minus h01. So this is the efficiency. So where the indicated enthalpies are stagnation values which take into account of the kinetic energy of the flow. The stagnation enthalpy can be defined as h0 is equal to h plus u square by 2. So this u is velocity of the flow. So this is the h0. So so now we'll solve an example which was asked in exam. So suppose this is the example. So calculate the open circuit voltage. So what we need to calculate is voltage, that is open circuit. So we need to find out E0. So that is open circuit voltage. And what is E0? That is BUD, as we know that BUD. So open circuit voltage and maximum power output. And what next we have to find out, that is P max. So P max also we need to find out. So P max, as we know that it is E0 square by 4 rg. So we need to find E0 first to find out P max of the MHD engine with following specifications. The specifications are given. So what are the specifications? So first specification is plant area. So as area is A, so area is given as 0.2 meter square. Then distance between two plates, so that is small d, that is 0.4 meter. Then flux density, that is magnetic flux, that is B. Then average gas velocity, that is small u. And conductivity of the gas, so that is sigma. So all the terms are given. So we will start with E0. So E0 is BUD. So what is B? So E0 will be equal to, B is 2 into U is 1000, 1 2 3, and D is 0.4, so into 0.4. So the open circuit voltage E0 will be equal to 800 volts. So it is 800 volts. So now we need to find P max. So P max E0 we have for P max, but we don't have RG, that is resistance. So generator resistance we need to find out. So what we will do? So we will so the formula for finding RG is, it is RG is equal to, what is RG is equal to D, small d, upon sigma A. So the distance between the plates, that is 0.4, divided by sigma A. Sigma is 10 move per meter into area is 0.2. So it is so it is 2 by 10, so it is 0.2. So it will come 0.2 ohm, 0.2 ohm. So we got resistance as 0.2 ohm. So now we will find out Pmax. So Pmax will be equal to 800 square divided by 4 into 0.2. So this will be equal to 800 kilowatt. So this is equal to 800 kilowatt. So this is the Pmax value. So the both terms which we needed to find out, we have found out, is Pmax and E0. So this solves our problem. So I hope you understood. So now we'll see few of the advantages and disadvantages of MHD power plants. So what are the advantages and disadvantages? So advantages of the MHD power plant. So first is MHD steam hybrid plant is highly efficient. So the efficiency is very high, nearly equal to 50 to 60 percentage. So the fuel is better utilized. The second benefit is that the system has no moving part, so hence it is more reliable as it has no moving part. Then the third is that the closed cycle system produces power free of pollution, so no pollution in closed cycle system. Then fourth advantage is that the MHD generators have low specific weight. So the specific weight is low. So it will result in rapid start. So rapid start, high power density. So P by V is high power density, and compact. So then fifth point is all kinds of heat resources such as coal, oil, gas, solar, nuclear can be used with the MHD generators. So all resources can be used with MHD generators. So it is also a good sign. Then the sixth is that it has ability to reach the full power level instantly. So the to reach full power instantly, so it is also an advantage. Then seven, the operational and maintenance costs are low. So the operation and maintenance cost are low. Then eighth, but thus the cost of power generation per unit is also less. So as the operation cost is low, so the power generation cost will also be less. Then high capacity MHD generators are possible as there is no limitation to the size of the duct. So no limitation in size of the duct. So the much more capacity you want, you can build. So the capital cost of MHD plants are estimated to be competitive with those of coal-fired and steam power plants. So the cost, this capital cost, is competitive, means it is more or less the same of the coal power plant. So it is also an advantage. So now what are the disadvantage? So we'll see disadvantages. So the first disadvantage is that MHD equipments have a shorter life due to high temperature stresses. So the life is shorter. So this is a big disadvantage. Second, it has high fluid friction losses and heat transfer losses. So losses are high of friction and heat loss. That is friction, and second is heat loss. So the losses are high. It has very high operating temperature. So the operating temperature is very high to maintain. So that is also a disadvantage which restricts the choice of material for various equipments. So the choice is restricted and high cost equipments are to be bought. So there are technical limitations on enhancing the fluid conductivity. So the fluid conductivity you cannot enhance, and the strength of the magnetic field. So that is sigma and b, you cannot increase. So there is a limitations in increasing both. So these are the few disadvantages. Now we'll see few design problems and developments which are being faced in MHD, that why it is not generally widely used everywhere. So MHD design problems. So what are the MHD design problems? So for economical and practical use of MHD generation, we will consider few problems. So MHD generator channel. So MHD generator channel combustor electrodes and air preheater are exposed to corrosive combustion gases. So all channel combustor electrodes and air preheater all are exposed to corrosive corrosive combustion gases. So what will happen, and this also at very high temperature. So what will happen to this? So the materials must be developed to permit an adequate operating life for the components. So few components need to be developed. So components need to be developed which will have a high operating life due to this environment. So the ash or slag residue from burning coal is carried over with the combustion gases and tends to cause erosion of the exposed surface. So however the deposition of the slag, so the deposition of the slag on such surface may provide some protection. So it may provide some protection due to the slag. Uh, Another problem is separation of the seed material. So that is potassium sulfate, K2SO4. So potassium sulfate from fly ash and its reconversion into the original carbonate. So into reconversion of the original carbonate form, and the difficulties associated with the slag and seed recovery can be eliminated by using fuel gas derived from coal rather than coal itself. So we should use fuel gas from the coal rather than using the coal, so in the combustor open cycle system. So a more advanced concept is to use hydrogen gas. So to use H2 gas uh, made from coal and water. So if we use H2 gas from coal and water, coal plus water, when this is burned into oxygen, the product would be a high temperature steam. So after seeding and passage as working fluid through the MHD generator, the steam would be used to drive a turbine generator, thus avoiding the need of waste heat boiler. So the waste heat boiler will not be required because as after seeding and passage are as working fluid, so the MHD generator, the steam would be used to drive the turbine generator only. So the boiler will not be required. So the power output So the power output of an MHD generator is theoretically proportional. So power output of the MHD generator is theoretically proportional to the square of the magnetic field. So P is proportional to B square. Hence the strong magnetic field is desired. So superconducting magnets which use very little current will be necessary. So this is the main design problem and in the development of MHD. So materials are required very much high. So we will discuss materials and prospects of the MHD generation in the next lecture. So thank you very much. Hey guys, my name is Mukesh Ahuja and we were discussing magneto-hydrodynamic power plants in the subject of renewable energy engineering. So in that we have seen few design and development problems for developing MHD power plants. So the main issue for developing the power plant is that the material selection becomes very crucial because the material life gets deteriorated due to the gaseous gaseous forms ionized gas which will move inside the generator, so due to which the material becomes very much important factor. So today we are going to discuss what kind of material is required for MHD generators and why this power plant is not widely used because of its materials. So the materials used in the construction of MHD plants must have first, as you know that this power plant works on very high temperature, therefore high temperature resistance means it should withstand very high temperature and should not melt on or should not deteriorate on high temperature. So its life cycle should be high. Also high temperatures combined with high temperatures plus alkaline atmosphere. Also alkaline atmosphere due to presence of seeding materials makes this MHD duct extremely susceptible to corrosion. So due to this atmosphere, it can be suspected to corrosion. So the selection of the materials is very limited due to the stringent environmental conditions. So the important factors to be considered for the selection of materials are, so first as we have seen is high temperature resistance, second is alkaline atmosphere, therefore we can say it as corrosion resistance. Third we can say is that electrical conductivity, that it should be conductive. Then fourth is erosion resistance, so the material should not be eroded. Eroded means that the particles should not be removed due to the movement of the gaseous particles of high velocity, so it should be erosion resistance. Then fifth is its melting point of the materials, so the melting point of the material should be very high, so it is very much important. Then sixth is oxidation reduction resistance, means oxidation and a reduction, that as we know that there may be possibility of oxidation and reduction, means oxygen and hydrogen So therefore it should be inactive towards the oxidation reduction. And seventh is its density, so it should be denser. So these are the main characteristics which are required for the material. So to obtain such kind of material is very much difficult, and very limited criteria are there to select this material. So now we will see the other materials which are required in the power plant. So the other components which are required. So which are the components? So let's see for that electrode. So suppose the high conductivity, high temperature is required for this electrode. So the material should be electrically conductive, structurally stable at high temperature. Refractory materials like nitrides, borides, and carbides are suitable materials. So for electrodes, this nitride, boride, and carbide can be selected. Second, for duct liner, which material we can select? So for duct liner, it is cooler than electrodes. So the materials must be both electrical and thermal insulator. So here electrode should be as you know conductive, but duct liner should be resistance to conduction, means it should be insulator. So electrical and thermal insulator. So it should be electrical and thermal insulator. So the insulating materials used for duct walls are magnesium oxide and strontium zirconate. So strontium zirconate and etc. So MHD ducts have to withstand a temperature in the range of, so they have to withstand a temperature in the range of 300 not but 3000 degrees Celsius. So presently steam cooled walls which are made of insulated laminations of very thin nickel or stainless steel have been tried. The research is on to use suitable ceramics or coatings of ceramics to use as duct materials. Third, so now what is third? Third is magnet. So it is stringier than permanent magnets. So ferromagnetic cores can be provided. Superconducting magnets can also be provided, which are very little current. So magnet for magnet ferromagnetic cores. Ferromagnetic cores can be provided, and superconducting magnets can also be provided. The superconducting magnets can also be provided with use of very little current. So these are the components where the materials are used. Now we'll see the future of the MHD power generation. There is future prospects that where MHD generation has potential and where the MHD generation is ongoing project. So we'll see the future of MHD generation. So the future of MHD generation. So the first 25 megawatt MHD pilot plant was commissioned in the erstwhile in USSR in 1970, which has successfully supplied electricity to the Moscow grid. It was followed by 1000 megawatt capacity plant 1000 megawatt capacity plant near Moscow in 1981. So a pilot 250 megawatt engineering test facility which is planned to be fully integrated MHD steam power plant is commissioned in USA. So a major countries involved with MHD activities are, which are the major countries? So there are Russia, USA, Japan, Australia, China, India, Italy, Israel, and Poland. So these are the 9 countries which are involved in MHD activities. So let's talk about India. So in India also considerable studies have been carried out in the field by a team of scientists under the National Council of Science and Technology, that is NCST. The Department of Science and Technology of Government of India has sponsored research and development program on coal based MHD power generation. This coal based MHD power generation. Then BARC, that is Baba Atomic Research Center, in collaboration with BHEL, this Bharat Heavy Electricals Limited, and Institute of High Temperature, Russia, is also executing research and development in the field. Under joint Russia program, a prototype MHD generator having 5 megawatt thermal input with coal gas as a fuel. So these are the institutes where the MHD generation programs are held. So in Russia, uh, it is executing research and development. So under joint Russia program in India, a prototype MHD generator having 5 megawatt thermal input with coal gas as fuel, which uses a seed of 50 percentage of K2CO3, that is potassium carbonate, in water has been built at Bhel. So this has been built at Bhel, that is in Trichy, Tamil Nadu, in collaboration with BARC, that is Baba Atomic Research Center, Mumbai. So MHD generation looks the most promising of the direct conversion techniques for the larger scale production of electrical power. So this is the prospects of the future power generation using the technology of MHD, that is magnetohydrodynamic. So as you can see that the main concern for generating the power is the selection of the material, because many properties are taken into consideration due to its very corrosive and very high temperature environment. Therefore the life of the material becomes very much important, because we need not to replace the material again and again, so it will create a very high cost, and also it will create very high, it will require many so much manpower. So the selection of the material should be very much important in this MHD power generation, due to which the gen- due to which the mainly the the popularity of this power plant is very much less, but also it may gain popularity when it shows much high good results because the initial cost of the materials will be very much high. So the we will also we have seen all the aspects of MHD power plant. So this was the last topic of the MHD power plant. So I will just revise once again. So which topics we have seen? So first we have seen the principle that works on the Faraday's law, that when an electrical conductor moves across a magnetic field, a voltage is induced in it which produces an electric current. So that is the Faraday's law. And then we have seen that force is induced, and we have then also seen that power output of an MHD generator, that how much output is there of an MHD generator. Then we have seen the thermal efficiency of the MHD cycle, and then also we have seen one example. Then we have seen open and closed cycle system, that is MHD systems is open and closed. And then we have seen advantages and disadvantages of MHD plants, that why what are the advantages, why it should be used. So there were many advantages, and the disadvantages are very less, but it is very much important. One or two are the disadvantages, but it has very much impact on the development of the MHD design. There is problem in design and developments. Then we have seen the then we've seen that magnetic field strength, that is power output of an MHD generator, is directly proportional to the magnetic field strength, that is B square. But the stronger magnetic field is desired for more power output, but it has some limitations for getting higher magnetic field. We have some limitations. So these are the concepts, various concepts and various topics you discussed. So now, and also then we have seen the future prospects of the MHD power generation. So this ends the chapter, and this also ends the non-conventional energy sources or renewable energy engineering. So thank you very much.